The premise of this presentation is that energy is a disturbance of space carried through matter and or space by universal expansion. Many animal species share in a feature called curiosity. Cats and dogs are curious, but human curiosity is different. We seek patterns in what we see, and the most consistent pattern is found in numbers. Although there are irrational numbers, think pi, numbers are normally cyclical, they repeat. Look at this, 5, 4 plus 1, 2 plus 3, 3 plus 2, 6 minus 1, 7 minus 2, 8 minus 3. This makes numbers valuable for predicting what path events will follow. Historically, numbers were not critical. Arithmetic and geometry were developed for surveying and other practical needs. Short of local trading use, numbers were not extensively used. The barter system only required basic arithmetic. Though technically advanced, Roman math consisted of a good understanding of geometry and basic addition and subtraction. Algebra, trigonometry, and calculus, these were unknown and useless to Romans. Egyptian and Babylonian astronomers created sundials based on the sun's motion. And with an understanding of buoyancy, Archimedes was able to determine if a crown was made of gold and why ships float, while Eratosthenes measured the Earth's diameter over 2,000 years ago. With Newton, Kepler, Galileo, and Carnot, mathematics bloomed in physics. But mathematics was used to explain observations. Observation always came first. So, for example, Newton determined that a force determines the acceleration of an object. To Kepler, the orbit of a planet was an ellipse. Galileo thought that regardless of weight, all objects fall at the same rate. And Carnot realized that the conduction of heat is irreversible. Alongside this advancement in mathematics, scientific terminology became more exact. Electricity, acceleration, heat, velocity, forces, and other terms were precisely defined, and those definitions were appropriate for their time and usage. But other terms were circularly linked to each other. So, for example, matter is anything that has mass, and mass is a property of matter. No explanation for what matter is or mass is. Work is equal to energy. Energy is a property of matter. The usefulness of these terms lay in their practicality and the fact that they could be calculated. Now, this topic is about energy. And energy has been classified depending on matter. Electric energy is energy of moving charged particle. Thermal energy is energy of randomly vibrating atoms and molecules. Kinetic energy is energy of large moving objects. Chemical energy is energy in bonds, and other types of energy. But kinetic energy can't exist without large masses. And thermal energy can't exist without atoms and molecules. And electrical energy can't exist without electrons. And chemical energy can't exist without the bond between atoms. But all forms of energy can change from one into the other. So upon impact, a falling ball converts its kinetic energy to heat. A burning object converts its chemical energy to heat. Electrical energy in a light bulb eventually turns to heat. And even nuclear power from an atom center becomes heat. But regardless of what type of energy we discuss, all forms of energy eventually become thermal energy. And our understanding of thermal energy is summarized in the 3 laws of thermodynamics. These 3 laws were derived specifically for heat energy and work. The first law states that energy cannot be created or destroyed. Obvious. The third law states that energy input always exceeds output. In other words, you can't create a perpetual motion machine. As a matter of fact, you can get out the amount of energy put into something, you always get less. The second law of thermodynamics, most interesting I find, is that energy cannot be contained, it must escape. So a hot liquid in an insulated container eventually cools to ambient temperature. And as energy escapes confinement, it moves matter, it creates disorder. And we call this disorder entropy. So the second law of thermodynamics is usually called entropy. How fast heat escapes the container depends on the substance the container is made of. We call this the substance thermal conductivity, and we assign the letter K to it. And every substance has a different K, as you can see from the table next to it. But regardless of thermal conductivity, heat energy cannot be contained. Even if you place the container in space, when heat reaches the container's outer surface, it radiates away as infrared radiation, a type of electromagnetic energy. And if the container is exceedingly thin and the content extremely small, thermal energy would theoretically instantly escape as infrared radiation at the speed of light. So without the restraining effect of matter, heat energy would change to electromagnetic radiation and move at the speed of light. So apparently all forms of energy decay to heat energy, which is energy of moving atoms and molecules, but heat itself escapes from matter as infrared radiation, a type of electromagnetic radiation. So what is electromagnetic radiation? If charges are placed on an object, the object will have an electric field around it. If charges on a conductor move at a constant velocity, a magnetic field forms around the conductor. In both cases, the electric and magnetic field are static. If a high voltage alternating current is applied to a conductor, the energy used to charge the conductor is carried away from the conductor as electromagnetic radiation. And Google defines electromagnetic radiation as energy waves from accelerated charges. So in an antenna, high voltage alternating current accelerates electrons back and forth, creating radio waves. In a microwave oven, electrons are accelerated inside a magnetron, creating microwaves. And even in an atom, electrons fall to a lower energy level, creating light of different energy depending on which shell they fall through. Let's set up an analogy. As pointed out, charges standing still or moving at a constant velocity do not create electromagnetic waves. Similarly, a speaker in a flying aircraft or moving car makes no sound. But when you apply a changing voltage to the voice coil of a speaker, that accelerates the diaphragm back and forth and creates a sound wave. Well, the antenna is the same. When you accelerate electrons, they behave like a diaphragm of a speaker and create electromagnetic waves. And in both cases, electrical energy is being changed to sound wave or electromagnetic waves. Although electromagnetic energy needs matter for its creation, needs accelerating electrons, electromagnetic waves are independent of matter as we know it. Because of this semi-independence, I like to classify electromagnetic energy as pure energy. Question is, do we need accelerating charges to create electromagnetic waves? The answer is no. All neutral atoms can produce electromagnetic energy, infrared radiation, and in a collision between neutron stars or black holes, electromagnetic energy is released as what we call gravitational energy. But both types of energy are electromagnetic energy because they both travel at the speed of light. Newton and others saw mass, space, energy, gravity, and time as independent entity. Einstein folded these concepts into two theories, the special and the general theory of relativity. In his belief, Einstein believed that mass and energy were the same thing, but they're not. Matter can be collapsed into a black hole, but if you concentrate energy, you merely create particle-antiparticle pairs. Matter and energy are two different entities. They're related to each other, but they're different. Question: how does universal expansion treat mass and energy? Well, I believe that universal expansion can't accelerate a massive object. It can't move masses by itself. But energy doesn't have mass. Therefore, universal expansion can move energy at the speed of light, the speed at which the universe itself is expanding. Now I'd like to qualify the statement. The creation of spacetime jiggles subatomic particles continuously, which means you can't measure position and momentum of a subatomic particle at the same time. It's called Heisenberg's uncertainty principle. So why can't universal expansion move mass? Well, unless it's accelerated by a force, every object, every mass is stationary relative to itself, a truism. In an object's frame of reference and moving and away from other masses, away from gravity, space expands equally in all directions. So we can think of universal expansion as a balanced force, and balanced forces don't move objects. According to relativity, regardless of force, no mass can be accelerated to the speed of light. The speed of light is the ultimate speed limit for mass. Again, why? Well, when a force is pushing an object, the object moves. And when the force stops, universal expansion acts as a three-dimensional conveyor belt. In other words, universal expansion carries masses at whatever the final velocity was and in whatever direction they were going to. And we call this inertia. Well, objects can reach light speed because universal expansion only carries objects at the velocity that the force propelled them. And nothing in nature can exceed the conveyor belt's velocity. But by definition, electromagnetic waves have momentum but not mass. Therefore, universal expansion can carry all electromagnetic waves at the conveyor belt's speed, the speed of light. Why? Well, Aristotle believed that everything must stop. We believe that unless a force is applied, everything moves at a constant velocity. Apparently, the universe prefers constant velocity. So let's return to the sound wave analogy. When a speaker's diaphragm vibrates forward, that's an acceleration, it compresses the air. The air is compressed, not given forward velocity. A supersonic plane moving at supersonic speed compresses the air in front of it, but doesn't give that air or the sound a forward velocity. And when the speaker's diaphragm moves backwards, it rarefies the air in front of it. And the air is rarefied, not given backwards velocity. And every compression is followed by rarefaction. The forward and backwards impetus are equalized. They're equal. They're the same. And yet, the energy that created the compression and rarefaction moves forward in a three dimension as a sound wave. Sound being a disturbance in the air, traveling through air or water or solids or whatever. But air is a medium. What exactly propels the sound? Let's return to heat energy for a moment. The energy of a heated substance in a sealed container moves outward. And that's the second law of thermodynamics. The container's atom vibrates, thereby transmitting the energy outward. When the vibrations reach the container's outer atoms, some vibration energy is changed to infrared radiation. Now, we can easily visualize a speaker's diaphragm vibrations creating sound waves in the air. And we understand how electrons dropping to a lower energy level release energy. But how does the energy of vibrating atoms with electrons in the ground state, how does that create infrared radiation? It is well understood that accelerated charges create electromagnetic waves, and these waves carry energy away from the charges. The video on the right shows a dipole antenna receiving radio waves. As the waves go by, the electrons are moved back and forth, and the orange area is the electric field going up and down because of the charges on the dipole antenna. So if you want to create a sending antenna, you just replace the resistance, the R, with a high voltage alternating current. Notice the similarity between a speaker and this here. As the voltage increases, the wave rises. But what is carrying the wave energy away from the antenna? I believe the answer may be that universal expansion moves the energy at the conveyor belt's velocity. Literally, as the wave is being formed, universal expansion pulls her away. But matter interferes with the velocity of mechanical waves. Therefore, in the case of sound wave or water waves or what have you, matter interferes and prevents these waves, this energy from going at the speed of light. Of course, being independent of matter, radio waves are moved by universal expansion at light speed. Do waves travel in straight lines? Well, in the absence of forces, matter moves at a constant velocity in one direction, in straight lines. But waves of all kinds diverge in all directions. Even a laser, which collimates light, makes light go in one direction only. It still diverges, laser light still diverges. This may be due to an accuracy problem during the manufacturing stage, or maybe it's a feature of universal expansion. Light energy must expand in 3 dimensions. So what is energy? Well, nothing can move under its own power. And to accelerate matter, an unbalanced force is required. Universal expansion behaves as a balanced force. It can move object. But when an object is accelerated, universal expansion becomes unbalanced and carries the object forward at the same velocity and direction. But energy, being a disturbance of space, is carried through matter and or space by universal expansion. And universal expansion carries energy through matter at subluminal speed, at less than light speed. But away from matter, universal expansion carries energy at light speed, the speed of universal expansion.